So it turns out you don't have to have two slits to get an interference pattern. There are single slit interference patterns, but they tend to be a lot fainter than diffraction gratings and double slits because there's only one slit for the light to go through, right? If you look at the situation where the light's just going straight through, you'll get at 0 degrees, right? This is our angle from the side, right? At 0 degrees, the light goes straight through, and you get a bright spot right in the middle. Okay. Now, if you pick some angle such that this is one wavelength, right? The additional distance at the light in the top of the slit or the bottom of the slit, if it's the angles the other way, is one wavelength. Then you get a situation where you've got the middle of the slit is a half a wavelength difference in distance to this whatever this target is, right? The bottom of the slit is 0 wavelengths, right? The top is 1 wavelength, and so the light in the middle cancels out the light from the top and the bottom. So you get dark like that, right? So that's this spot right here. Okay, so sine of theta is lambda over d, and d is this width of these slits, right? Okay. And then if you go until this is, the angle goes further out, right? If you go until this is 3/2 of the wavelength, well, now you've got the light in the middle, okay? And these guys, 1/2 and 3/2, right? The light at the bottom here is about 1/2 wavelength, right? 1/2 and 3/2, that's constructive interference because there's one whole wavelength difference. And this is destructive interference. So you get a very faint maximum, and then you can just keep doing this argument, right? And you'll get a minimum and a maximum like that. So the pattern looks like this if you look at it in a circular sense, right? So here's the middle of it, right? There's that spot right here, right? And then here's the first minimum, which is here, right? Then you have the first, you really can't see that, sorry about that. Then you have the next maximum here, right? And so if you make this pattern circular, this is what it looks like, okay? Now, the reason why I'm talking about circular is that if you have a telescope, the light from a distant star shining through that telescope will cause this diffraction. These are called, I think, the Airy disks or something like that, right? It'll cause this diffraction pattern. And this is a basic limitation of any telescope, is that you have this diffraction pattern, which makes it, if you zoom way in on a star, it makes it hard to tell whether there's one star or two stars, and we'll look at that. But this is an inherent thing. It's, by the way, also, if you want to see whether the optical system in the telescope is working properly, these circles should be absolutely perfect circles and concentric, et cetera, et cetera. And if they're not, there's something wrong. A mirror's not ground correctly or something. I mean, I'm not knowledgeable enough to tell you exactly what's wrong with it. This is our formula, basically, is that there's this central maximum, which, by the way, is wider than, it's twice as wide angularly, okay, as any of the other maxima, right? These guys are only lambda over d wide, but this one is actually goes from minus lambda over d to plus lambda over d. And this is sine of theta equals this, right? Okay. And this formula is not really in the data pack. It's kind of sort of there, right? Only it's like d sine theta is n lambda is the maxima for double slit. For this guy, it's the minima. It's where these guys occur, okay? Yeah, that's all I've got to say.